The simple gas laws are gas laws that look at two of the four gas variables at a time, while the other two are being held constant. So the four gas variables are pressure, volume, temperature, and amount. Pressure is P, volume is V, temperature is T, amount is N. That amount has to be in moles, not grams, because 1 mole of hydrogen has the same amount of stuff in it as 1 mole of oxygen, which has the same amount of stuff in it as 1 mole of krypton. But 1 gram of hydrogen does not have the same amount of stuff as 1 gram of oxygen, so on and so forth. So your amount is always in moles, and again, it's in N. In order to see how two of these variables relate, for example, how pressure and volume relate to one another, the other two have to be held constant. Because if I'm trying to see how pressure and volume relate to one another and I'm then changing the temperature, well, the temperature has an effect on the pressure and volume. And I can't see how those two are related to one another. So you will look at the relationship between two while holding the other two constant. So thinking back to kinetic molecular theory, as the volume of a container decreases, the pressure is going to increase. Why does this happen? Because pressure comes from collisions. So if there is less space for the gas to move around in, there's going to be more collisions. More collisions means a higher pressure. As the volume of a container increases, the pressure is going to decrease because now there's more space for those gas particles to move around, which means there's going to be fewer collisions. So they go opposite. As volume goes up, pressure goes down. As pressure goes up, volume goes down. So pressure and volume have an inverse or indirect relationship. Mathematically, you represent that as multiplying the two variables. So pressure times volume equals some constant K. So if K is 8 and my pressure is 4, my volume has to be 2. If I then change the pressure to 8 in order to keep that constant 8, then my volume has to go down to 1. So my pressure went up, my volume has to go down. And so the way we represent this with a formula is P1V1 equals P2V2. P1 and V1 being the initial pressure and volume of the gas, and P2V2 being the second volume and pressure of the gas after you've changed one of them. This relationship is proportional, so if the volume is doubled, the pressure is cut exactly in half. Just like the example I just kind of verbally did, where if the pressure was 4, the volume is 2, that gives me my constant 8. If I double the pressure to 8, then my volume is cut in half to 1. This is what's happening in this picture here. So my initial volume is 1 liter, my initial pressure is 1 atmosphere. If I then cut the volume in half, the pressure is going to double. Using that guess method, we're going to look at what we're given. So we're given 2.75 liters. That's a volume. We're given the atmospheric pressure of 1.02 atmospheres. We increase the lung volume to 3.25 liters. What is the pressure in his lungs? So that's another P. So when I have volume and pressure, again, it's an inverse relationship. V1, P1 equals V2, P2. It's a good idea to write out what all of your variables are, just to kind of help you keep track of where stuff is. 2 is 3.25, and then P2 is my unknown. I like to rearrange the equation to solve for the variable first. If you want to just plug into the initial equation and then solve, that's fine as well. So P2 is going to be V1, P1 over V2. So that's going to be 2.75 liters times 1.02 atmospheres over 3.25 liters. Unit of liters will cancel. And so when I solve for my pressure, my unit is going to be atmospheres, and it's going to be 0.863 atmospheres, 3 sig figs, because everything I was given was 3 sig figs. Now looking at the relationship between volume and temperature. As temperature of a gas decreases, volume decreases. Now this has to be a flexible container. Think something like a balloon, something that can pretty easily change volume. As the temperature of a gas decreases, There's less movement, less particle movement. They have less energy. Yeah. Movement equals fewer collisions. So if there's fewer collisions in a flexible container, that means the size of the container is going to get smaller, because in a flexible container, those collisions, instead of increasing the pressure, collisions will actually just push the size of the container outwards. As temperature increases, volume goes up. There's more movement of the gas particles, more energy. So there's more collisions. Formula for this one, they have a direct relationship. As one goes up, the other goes up. Mathematically, this is represented as a fraction. So let's say K, my constant, is still 8. So if my volume is 16, my temperature is 2. That gives me that constant 8. If I double my volume up to 32, my temperature has to double up to 4 to keep that constant of 8. So the formula is V1 over T1 equals V2 over T2. My initial volume over my initial temperature equals my new volume over my new temperature. This relationship is proportional, but only if the temperature is in Kelvin. So it's very important for any law involving temperature that your temperature must be in Kelvin. So if the Kelvin temperature is doubled, volume is doubled. If I go from 100 Kelvin to 200 Kelvin, my volume will double. If my Celsius temperature is doubled, volume is not doubled. It is increased, for sure, but it is not doubled. Because doubling Celsius temperature is not the same as doubling Kelvin temperature. If I go from 100 Celsius to 200 Celsius, I'm going from 373 Kelvin to 473 Kelvin. Definitely not doubling. Increasing for sure, but not doubling. It's important to use a balloon because a balloon is a flexible container. A balloon can change volume. And so you can see in the ice water, the particles don't have as much energy. There's fewer collisions with the walls. The collisions aren't as forceful. And so it's kind of shrunken down. Whereas in boiling water, those particles are moving a lot. They have a lot of energy. There's a lot of collisions. The collisions are very forceful, and that's going to push the sides of the balloon out. So again, using that guess method, I have a volume of 2.8 liters. I have a temperature of 0 degrees Celsius. My volume decreases to 2.57 liters. And then what was the initial temperature is my unknown. So be careful when you're doing these problems. Make sure you're reading the problem and paying attention to what it's asking for, and not just plugging numbers in the order you see them. So my equation is V1 over T1 equals V2 over T2. V1 is going to be 2.8, but T1 is my unknown because it's asking what was the initial temperature. And if you read up here, we have 2.8 liters at an unknown temperature. So we don't know the temperature of that 2.8 liters. That's my unknown. V2 is 2.57 liters. T2 is 0 degrees Celsius, but you can't use degrees Celsius in these gas laws. You have to convert it to Kelvin, so it's 273 Kelvin. So solving for T1, we're going to get V1 T2 over V2, or you can just plug into the initial, original formula and solve that way. That's fine. So we're going to have V1 2.80 liters times T2 273 Kelvin over 2.57 liters, and I'm going to get 297. Again, the unit of liters will cancel, so the unit of that answer is Kelvin. This is also asking for the answer in Celsius. So Kelvin is Celsius plus 273. So Celsius is Kelvin minus 273. So just subtract 273, you get 24 degrees Celsius. In this problem, if the pressure exerted on a sample of a fixed amount of gas is doubled. So we're saying that we're not changing the amount that's being held constant. It says it's at constant temperature. So if the pressure is doubled, that means the volume is cut in half because they are inversely proportional. Then, so we have half the amount, then the temperature of the gas in Kelvin is doubled. Well, if temperature doubles, volume doubles. So what happens, or what is the final volume of the gas? It's actually the same as the initial volume. It got cut in half, and then it got doubled, so it's back to what it was before. Lastly, we're going to look at volume and amount. So equal volumes of gases contain the same number of particles. It doesn't matter if I have 3 liters of hydrogen or 3 liters of argon or 3 liters of oxygen or 3 liters of xenon. They all have the exact same amount of particles. The identity of the gas doesn't matter. Again, thinking back to kinetic molecular theory, as amount of gas decreases, volume will decrease. There are fewer particles, so there are fewer collisions. Again, we're in a flexible container here, something like a balloon. Anytime you're changing volume, it has to be a flexible container. As the amount of gas increases, the volume will increase. There are more particles, so there are more collisions. So this is, again, a direct relationship. So V over N would give me my constant. My formula V1 over N1 equals V2 over N2. This relationship, again, is proportional, so if the amount of gas is doubled, volume is also doubled. Doing a problem with this one, we have a male athlete in a kinesiology research study has a lung volume of 6.15 liters, that's a volume, 0.254 moles, that's my N, or moles is N in these. It decreases to 2.55 liters, that's a volume, and it's asking for how many moles of gas did the athlete exhale. So that's, again, moles is N. So my formula that involves V and N is V1 over N1 equals V2 over N2. V1 is 6.15, N1 is 0.254, V2 is 2.55, N2 is my unknown. If you want to just plug into that formula as is and solve for N2, that's fine. Or you can rearrange. So N2 is V2, N1 over V1. Oh, I guess I need to rewrite that again. Let's plug in the numbers. So V2, 2.55 liters, 0.254 moles over 6.15 liters. Liters will cancel. I get 0.105 moles. But it's really important that you understand what these numbers mean, what they stand for, all that stuff, not just plugging in and, oh, here's an answer, I'm done. The 6.15 liters was the initial volume of the lungs. Initially, the lungs contained 0.254 moles of air. The volume of the lungs then decreased to 2.55 liters. So what I just solved for is actually how many moles of air is left in the lungs. It's the new amount of air in the lungs. And that's not what the question's asking. The question's asking how many moles of air did the athlete exhale? And so I would have to take my initial moles minus what's left to solve for what was exhaled. Last question here. What action causes the volume of a gas sample to increase? Decreasing the pressure, decreasing the temperature, decreasing the number of moles, or none of the above. So we're looking for volume to increase. Think about these relationships and what's an inverse relationship and what's a direct relationship. So both temperature and moles are direct relationship. Decreasing those is going to decrease the volume. But pressure and volume are inverse. So if I decrease the pressure, that's going to increase the volume.